Alright, so in the previous video we have used the example to illustrate the problem we are starting here, right? And we can provide the formal description of the problem again here in this page. Formally, let's assume we have a query input and we use the joins as an example here. So given a query input with the R1 joins, R2 joins until Rn, right? We want to calculate the joins among all the relation inputs. And here we want to do the queries, optimizations, and we want to find the base join trees for the query. And we have an assumption here. So we assume we have a function, which is a cost function, which can provide us with the cost of every join trees. So given a join tree, we can use this cost function to estimate the cost of the join trees. And the target we are doing here, we are starting here, is to find the base join trees for the query inputs. Just similar to the previous pages, we have different formats for defining the join trees. Right? And we want to find the base join trees for this query inputs. And this is a target for the problem we are studying here. And we have different algorithms to be used for optimizations we mentioned before. Right? Here we are studying this problem based in the dynamic programming state. So general idea for the dynamic programming based query optimization algorithm is like this. So given the inputs, this relation R1 to Rn, right? So for each subset of the relations, we want to calculate or compute the base plans for such subsets. So it means given a subset of the relation, we want to find the base way for computing joins among them, right? As we have more inputs of the relations, then we can find the way to organize the trees by attaching more branches or nodes to the trees. So we can do this computation in an increasing order of the set cardinality, right? So step 1 we have here will be based on the relations, individuals, right? So we have R1 to Rn as individual relations. So then based on this kind of step 1, we can calculate the join cost for them, right? And then we can further increase the size for these subsets by incorporating more subset into them. Therefore, we have step 2. It will be for the subset we're covering 2 relations, right? We have R1 and R2, R1, R3, and Rn minus 1 and 2 Rn, right? And we can calculate the base plan for computing them at the same time. And as we increase this, until step n, we will calculate the optimal base plan for the joins among all the relations, right? So you can see, from step 1 to step 2, we increase the size for the subset of the relations by 1, right? And finally, we have the step n, this relation subset will cover all the relations in the input. So, this algorithm we're working as a bottom-up strategy. Given the individuals first, we can combine them step by step by incorporating more relation into them, right, for joins. So finally, we will be able to find the base way or base plans for computing the overall joins among all the relations. This is a high-level idea for the dynamic programming-based query optimizations. You can see, in this way, we will be able to not only find the optimal plan for the overall all these n relations, we can also find the best way for computing any subset of the relation for computing the joins at the same time, right? Because we have the records for the process, and for all the intermediate results, we have the codes for computing their joins. Right. In other words, we can have the best way for computing all the joins for any relations in this state according to this algorithm. So in this way, we can work as a bottom-up strategy to find the best way for computing the joins among the input relations. Okay, so these are high-level ideas, and we will show you with more detailed information how to implement this algorithm.